everyone, and welcome back. My name is Mr. Kovold, and in this video, we're going to calculate the freezing point depression of various substances and put them in order. So let's get into this. Okay, so for this video, we're going to calculate the freezing point depression. And so in order to do that, we need this equation right here. So this equation tells us that the change in the freezing point temperature is going to be equal to the Van't Hoff factor. We saw that before, multiplied by molality, multiplied by the freezing point depression constant of whatever the solvent we're looking at. In this case, the solvent is water. And so the freezing point depression constant for water is 1.86. So let's go ahead and do this. Also, by the way, the units here are degrees Celsius per molal. Okay, so let's go ahead and get started. Now, we have the freezing point depression of water, and so all of these are dissolved in water. And so we are given the molality of each of these, so we got that. What about the Van't Hoff factor? So here, the Van't Hoff factor is going to be related to the number of particles that are dissociated or dissolved in the solution from the substance that we are given. So here, for glucose, since when you put glucose in water, it doesn't break apart, therefore the number of moles of the particles in the water is going to be equal to the number of moles of the substance or that you're given. So in this case, the Van't Hoff factor is going to be 1. So I is going to be equal to 1. For NaCl, for every mole of NaCl that you put into water, you're going to get 2 particles, sodium ion and chloride ion. So the Van't Hoff factor for this one is 2. So I equals 2. Now, for this is an acid. This is hydrocyanic acid. This is a weak acid. It's not one of the strong acids. So therefore, it's not going to completely ionize in water. It's going to ionize a little bit. So even though when you put this in water, you'll get, 2 things like H plus ions and Cn minus ions, this is not going to completely ionize in water in the same way that NaCl will completely dissociate in water. And so that means that the Van't Hoff factor for this one is going to be between 1 and 2 because it's not exactly like glucose. Glucose, again, is not going to dissociate. It's not going to break down in water into smaller particles like NaCl is. But it's not going to completely dissociate like NaCl does. So it's going to be somewhere between 1 and 2. So probably closer to 1. So it's going to be 1 and 2, somewhere in between 1 and 2. And then for magnesium chloride, when this dissolves in water, we'll get 1 magnesium ion and 2 chloride ions for every one of these formula units. So that gives us a Van't Hoff factor of 3. So if you use this, you can calculate the temperature, the freezing point depression of each substance. Now, for this one, we don't exactly know what the I is, but we know it's got to be between 1 and 2. It's not equal to 1. It's not equal to 2. So it's somewhere in between here. So we can go ahead and calculate this for the other 3. So for glucose, your delta T of freezing, your freezing point depression is going to be equal to 1 times the molality, which is 1.0 molals times 1.86 degrees Celsius per molal. Molals cancel out, and you get 1.86 degrees Celsius. So that's going to be excuse me, that's going to be how much it depresses. So it's going to decrease by 1.86 degrees Celsius. We do the same thing here. This time the Van Hoff factor is 2. That's going to be multiplied by 1 molal times 1.86 degrees Celsius per molal. And then that gives you double this amount. So that's going to be 2 times 1.86. That's going to be 3.72 degrees Celsius. So in that case, your freezing point depression is going to be decreased. The freezing point is going to decrease by 3.72. So that's double the amount, which makes sense because you're doubling the amount of particles compared to that of glucose. We'll skip the HCN for a moment. We'll go to magnesium chloride. So the delta TF there is going to be the Van Hoff factor is 3 multiplied by 1.0 molals times 1.86 degrees Celsius per molal. And again, we're going to have 3 times as much. So that's going to be, let's see, 1.8. So that's 1.8. That's going to be 5.4, 5.5, 5.58 degrees Celsius. So that's going to be how much it depresses. So your freezing point is going to depress by 5.58 degrees Celsius. Since the freezing point of pure water is 0 degrees Celsius at sea level, that means that this would freeze at negative 1.86. This would freeze at negative 3.72. And this would freeze at negative 5.58. And so for this one, since we know that the Van Hoff factor is somewhere between 1 and 2, that means that the freezing point here, the freezing point depression here is going to be between between 1.86 degrees Celsius and 3.72 degrees Celsius. Right, that much we do know. We could probably use a number. We know that because this is a weak acid, it's going to ionize just a little bit, a tiny bit. So then the Van Hoff factor for the hydrocyanic acid is going to be very close to 1, a little bit higher than 1. It's going to be closer to 1 than 2, right? So we can say it's going to be between here, probably closer to 1.86. But we don't need to calculate it out exactly because that's enough to answer the question, because we want to put this in order of the size of the freezing point depression. So the largest is going to be D, magnesium chloride. So the magnesium chloride is going to be the largest. It's going to have the largest freezing point depression, followed by the NaCl, and then followed by that of HCN, and then the least is going to be that of glucose. And that, ladies and gentlemen, is how you do it. Now, before I end the video, you actually didn't need to calculate all of this out, because what you should have noticed, or what you probably did notice, is that in this case, for all of these, you'll notice that the molality is the same for all of them, and the Kf value, the freezing point depression constant, is the same because the solvent is the same, water, right? So the only thing that would determine uh, the size of the freezing point depression is your Van't Hoff factor. So as long as you can figure out what the Van't Hoff factor is, then you could order them according to that. The larger the Van't Hoff factor, the larger the depression. So you actually didn't need to calculate it. I just went ahead and calculated to show you in case you wanted to calculate it. But if you notice this, if you notice that these were the same and the only difference was the Van't Hoff factor, then you just order it by the knowledge of the Van't Hoff factor based on the formula. So one of the probably the trickier things is to recognize this as a weak acid. So if you didn't realize that, maybe that might have thrown a wrench into the problem for you. But you have to recognize that this is not a strong acid, it's a weak acid. If it was a strong acid, then it would have the exact same Van't Hoff factor as NaCl, and it would give you the same freezing point depression as NaCl. But since it's a weak acid, it's not going to ionize as much as NaCl dissociates, so therefore it's going to fall between glucose and NaCl, and so that's where we get the order from. I hope this is helpful. If this was helpful, if you enjoyed the video, then please by all means like the video, share the video, hit that like button somewhere over here, I think. Also, make sure you subscribe to my channel. Help me out. It will help me out greatly. Also, hit that notification bell up there somewhere. When you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem you need help with, if you have a question that you can't solve, if you have a topic you want me to cover, let me know down below. I'm here for you. Thanks for joining me, and have a great day.